Uh, right, welcome everybody. Thank you for coming along to the U3A Communities Geology Group. I'm very proud and privileged to be introducing Dr. Simon Stephenson, who's kindly volunteered to come and speak to us about his work with Ascension Earth Sciences. Simon completed his PhD at Cambridge University, where he explored the impacts that can't even say the word, geophysical processes have on estimating sea level. And I believe he most recently worked as a research scientist at the University of Oxford, working in collaboration with Geoscience Australia as part of their Exploring the Future programme. Now, I've seen some of the websites for their museums out there, and they have some really good stuff to download. And people will be aware, Simon, that we have a couple of resource pages, and that includes some of the resources from them, so they can get hold of that information. Now, moving on to your current work as Head of Technology at Ascension Earth Resources. My understanding is this is a University of Oxford spin-off company that is working on ways to extract minerals in novel and more environmentally friendly ways. And that the work you're doing combines theoretical modelling with empirical relationships and machine learning to explore the formation and novel development of mineral resources. Now, if I've missed anything out, please do fill us in. And thank you for coming to speak to us, and I'll hand over to you.
Great. Thank you very much, Mary. That was a very, very nice introduction. So yeah, it's a privilege to be speaking with you today, and thank you very much for the invitation. I'm just going to share my screen. Hopefully, that'll be straightforward to do.
Wonderful. Yes,
You can see that, can you?
we can.
Okay, so I'm going to talk to you today about sort of my career in research and how it's led me to my current position at Ascension Earth Resources, which is, as Mary said, a spin-out company from the University of Oxford, trying to look at greener ways to mine for critical minerals without all the sort of deleterious environmental consequences that can be associated with mining if not done in an environmentally conscious way. So I've called this talk From Geothermal Heat Flow to Green Mining. And if you bear with me for a little bit to start with, I'm going to explain a little bit of the background to understanding geothermal heat flow and some of the research I've done over my career in research before I then talk about how this has led me to my position at Ascension and what we're doing there. So this is a picture of Ascension Island in the background here. I just got back from Ascension Island on Saturday, actually. It's a very, very interesting place if anybody does ever get the chance to go there or has been there, and I'll tell you a bit more about it later on. Okay, so I'm a geologist, and geologists look at rocks in the most fundamental sense. I'm also sort of moved over my career towards geophysics. And geophysicists do things like deploying instruments to image the subsurface in those places where you can't directly access the rocks. So my career has taken me to all sorts of places. So Madagascar, Spain, Ascension Island, and so on. And there's pictures here from all the way through my career from my PhD onwards. So my career started in Imperial College London, where I did my undergraduate at the Royal School of Mines. Before, as Mary said earlier, I moved to the University of Cambridge for my PhD, and I also had a short research position at the University of Cambridge as well after my PhD. Before, in about 2020, I moved to the University of Oxford, where I also hold a teaching position at University College Oxford. And this position was funded by Geoscience Australia, where this started my move towards the resources sector, where we're looking at how sort of global scale observations can inform better locating, can better locate mineral resources. And this really is where my jump off point was to join this spin out company, Ascension Earth Resources. So what I'm going to do, first of all, is just make sure we're all on the same page with the structure of the Earth, because this is going to come back a fair bit in this talk. So I've drawn this incredibly simple diagram here where we have in black the Earth's crust, which is something between 7 to 70 kilometers thick or so. And that sits on top of the mantle shown in pink here. And then inside that is the outer core, which is a liquid, and the inner core, which is a solid. And this talk is going to be concerned mostly with the crust and the mantle. Another way to think of that is that the outer shell of the Earth we can call the tectonic plate. Now, the tectonic plate actually doesn't just include the crust, it's also a layer underneath the crust as well. But it's quite thin relative to the diameter of the Earth. And yeah, there's the mantle. And the mantle is a solid. So everybody probably is familiar with the idea that the mantle can flow over time, but that doesn't actually mean it's a liquid. So its consistency is a bit like sort of warm plasticine or something. It flows at about the same rate your fingernails grow, and it sort of creeps along. But it's not a liquid. It's actually made of solid rock. And here's a lump of mantle rock, which is sort of by accident exposed at the surface that was collected. And then there's the outer core and the inner core. And my work has really been concerned with making observations of the surface to try and understand plate tectonics and the structure of the tectonic plate and the mantle. So I'm showing you here a simplified tectonic map of the world. I'm sure everybody's familiar with this kind of thing. So the Earth's outer shell is divided into these very large slabs of rigid material that sort of float around on this creeping mantle relative to one another. And they interact with each other. So, for example, the Indian plate is moving northeast. It's actually motoring along the Indian plate. It's probably the fastest moving plate in the Earth's history, perhaps. And where it hits into the Eurasian plate, the Indian plate sort of dives down under the Eurasian plate, and they crumple together and form these mountain ranges. Conversely, where these plates move apart, so for example, between Arabia and Africa, we have the Red Sea. The Red Sea is actually a brand new ocean, which is only a few million years old. The two plates are moving apart and we form these rifts. And a kind of incipient new rift that's forming is in East Africa. And maybe if we go back to East Africa in, say, 20, 30 million years' time, there might be a Red Sea in between Somalia and the rest of Africa, perhaps. And these are the primary mechanisms on Earth by which we can generate topography. And by that, I mean, where plates come together, we get uplift, so we get mountains being formed, and where they move apart, we get subsidence, so we get these rift valleys forming. And this can happen on a rate of maybe up to a centimetre or so per year. And it can actually happen very, very suddenly. So during an earthquake, we can get maybe a metre of movement on a fault, which can uplift the Earth's surface by a metre or so. But there are actually other mechanisms by which the Earth's surface can move up and down. And this is what I've been working on for most of my research career. So other uplift and subsidence mechanisms. And one of the most relevant in the UK is this issue of post-glacial rebound. So as I'm sure everybody knows, the northern hemisphere was covered in ice. Well, not the northern hemisphere, the far northern hemisphere was covered in ice during the last glacial period. So this was the period spanning from about 10,000 years ago up to about 110,000 years ago. So Scotland all the way down to around about Oxford, where I am today, was covered in ice in Britain. Also, most of Canada and northern USA, Scandinavia, parts of Siberia were all covered in ice. And what this does is, because if you remember the mantle can flow, the ice actually presses down on the surface of the Earth and causes the areas covered by ice to subside. And then when that ice melts, we get the opposite process happening. And the areas that were covered by ice shoot up over time. So, for example, parts of Canada are actually uplifting every year by about 10 millimeters or so a centimeter per year. So the coastline of Hudson Bay is really motoring upwards. And this is a map of Britain. The colours indicate uplift versus subsidence. So the green are regions that are uplifting. So Scotland and Northern England are uplifting at a few millimetres per year, and Southern England is actually subsiding at fractions of a millimetre per year. So if you walk around the coast of Scotland, sometimes you might see these sort of gravelly surfaces that are several metres above sea level, and those are often raised beaches. So they're regions that were actually at sea level that are now several metres above sea level. And why am I telling you all this? Well, it's indicating a property of the mantle, which is really important. So the mantle can flow, and as it flows, it actually moves heat around inside the Earth. So the core is hot, and it's hot because of how the Earth formed 4.5 billion years ago. And the mantle actually transfers heat from the center of the Earth to the surface of the Earth. And this has some quite interesting consequences. So this is a photograph from the Isle of Arran in Scotland. So if I go back to that previous picture, the Isle of Arran here is here in the Firth of Clyde. Is in the green colours here, indicating it's uplifting. And these are some sea caves on the Isle of Arran, which are now several metres above sea level. So there's no conceivable way that the sea could have eroded these caves today. They must have been eroded some time ago and since been uplifted. And interestingly, one of these caves is supposedly where Bonnie Prince Charlie was hiding when he was exiled. Now, really interestingly, and something I think a lot of people don't realise, is that the Thames Barrier in London was actually constructed because of mantle processes. So probably what a lot of people think is that the Thames Barrier was built to prevent London from being flooded under climate change. And that is no doubt a huge benefit of the Thames Barrier, because sea levels are rising as a result of changing climate. But London is also subsiding as a result of post-glacial rebound and as a result of basically just mantle processes. So there's a very practical application of understanding the mantle. And this was known in even the 1970s when the Thames Barrier was designed, the late 1960s, the Thames Barrier was designed. So London subsiding at fractions of a millimetre every year, but that means that over a few hundred years, London will subside by fractions of a metre, which will increase its risk of flooding quite substantially. So the Thames Barrier was built before much was known about human-induced climate change, and it was really built to protect against inundation due to post-glacial subsidence. So that's post-glacial rebound, and I hope I've demonstrated that understanding the mantle is actually quite important for some quite practical human reasons. There's actually another process by which the Earth's surface can go up and down. So to explain this, I'm going to go back to thinking about the Earth's crust. So if I take India and the Himalayas here, so in India, the Earth's crust is maybe 40-45 kilometers thick. In the Himalayas, the crust is maybe 80-85 kilometers thick. And I'm sure everybody is familiar with the idea when the crust is thicker, where we have these tectonic plates converging, mountains are higher. And sure enough, just to emphasize this point, in India, central India, the topography is maybe 300 meters high, and then in the Himalayas, we're looking 7 kilometers high. And if I plot a diagram now, so there aren't many of these kinds of diagrams, so just bear with me on this one. On the x-axis, I'm plotting crustal thickness everywhere in the world that we have a measurement against the elevation at that same location. And I hope you can see it's not a particularly, blow you away sort of correlation here, but there is a general relationship between higher crustal thicknesses. So if you look in this band 60 to 80 kilometers, there's no place on Earth where the crust is that thick and the topography is lower than a couple of kilometers high. Everything where the crust is 60 to 80 kilometers thick or so, the surface of the Earth is higher than 2 or 3 kilometers. However, if you go to a crust that's 20 to 30 kilometers thick, there's nowhere where the Earth's surface is higher than 2 to 3 kilometers. So this is indicating that as we're all sort of familiar with from the raw measurements, crustal thickness seems to be the main control on the height of Earth's topography. Just to emphasize that point, here's a couple of those points I showed you from India. So 35, 40 kilometers at sea level, and then 80 kilometers at 6 or 7 kilometers high. So that's emphasizing that point. And that's actually the way that topography is generated in most cases on Earth. But it's not the only way. So take North America, for example. Eastern North America in the Great Plains, the crust is about 50 kilometers thick. In Western North America, on the Colorado Plateau, crust is only 25 kilometers thick. So this is, if we look at the height of the topography here, this is almost exactly the opposite of what we just saw in India. So on the Great Plains, topography is only 100 meters high. On the Colorado Plateau, topography is about 2 kilometers high. So clearly, if we go back to this diagram here, that doesn't work anymore in this particular location. So in general, Earth's crustal thickness controls the height of the topography, but obviously not everywhere. So why is this? Well, I told you that because the Earth's mantle can flow, it transfers heat from the inside of the Earth to the outside of the Earth. And how it does this is with these kind of blobs of material. So what I want you to kind of think about here is two analogies. So one is a lava lamp. So a lava lamp has, I hope all of you are familiar with a lava lamp, has these sort of blobs of material. It has a heat source at the bottom and then it's cooler at the top. And it has blobs of material that detach themselves from the bottom and they flow upwards through the lava lamp until they reach the top and then they sort of subside again around the side. And the other is just simply a radiator in a room in your home. So if you put your hand above the radiator, you'll feel potentially a slight breeze above your hand as the air rises above the radiator and moves its way around the room. So what both of these analogies demonstrate is that hot material is lighter and likes to rise. And what the lava lamp demonstrates is that hot material, when it's rising from a sort of a hot plate, tends to form these blobs. And that's just the same in the Earth's mantle. We have these blobs of hot material that detach from the core and rise up to the surface. And conversely, we have these blobs or sheets of material that detach from the surface and sink downwards through the mantle. And both of these things are happening all the time on Earth. And what they do at the surface is really interesting. So where that blob of hot material rises upwards, it pushes up on the base of the tectonic plate, and it actually domes the surface. And where the dense material is sinking, it draws down the surface. So think of another analogy here. So when you pull the plug out of your bath, the water pours out through the plug hole, and you might notice that actually above the plug hole, okay, the water spins. Ignore that for a moment. The mantle's too viscous for that to happen. But what you'll also see is the water is actually depressed above the plug hole. So the surface of the water is actually drawn down where the water's pouring out of the plug. And exactly the same thing happens on Earth. Where this dense stuff sinks into the mantle, it sucks down the surface of the Earth, just like opening the plug in your bath. This also happens in the oceans, by the way, as well. So there are domes in the surface of the ocean where we have warm upwelling material, and there are sort of depressions in the surface of the ocean where the cold material is sinking. So maybe around Antarctica, for example. So this is quite interesting because these hot and cold blobs have a surface expression that we can measure at the surface. And this is what we call dynamic topography. And a lot of my work when I was in academia, in research, was around trying to understand this process of dynamic topography as a proxy for helping us understand what's going on inside the mountain. And what's quite interesting about this process is that it reveals something quite interesting about how the mantle behaves. So if any of you have heard of this idea of mantle convection before, this is this idea of transferring heat from the center of the Earth up to the surface of the Earth and transferring sort of cool material from the surface of the Earth back down to the center of the Earth, you might have this idea of mantle convection based on these ideas of convection cells. So this is where you have a hot thing that rises up to the surface because it's light and less dense. And then it sort of flows along a bit along the surface, and then it kind of sinks back down again, where we have one of these tectonic plates diving back into the mantle. And this is kind of consistent with that lava lamp analogy, isn't it? You have the hot material rising in the center of the lava lamp and then cooling and sinking around the outside. Or the radiator in your room, in your house, the hot material rises above the radiator, travels along the surface of the ceiling, and then sinks down the other side of the room. Unfortunately, it turns out from my research and many other people's research around the world, is actually not what the Earth looks like at all. It's actually much more complicated than that. So I'm going to put a big cross through this. Earth's mantle convection actually looks something much more like this. It's really complicated. So we have these funny sort of sheets of material diving into the mantle, which are really concentrated cold spots. Sometimes they dive and wrinkle, sometimes they sort of flatten off. And then at the bottom of the mantle, we have these plumes of material where hot material sort of concentrates and rises up in a very, very, very narrow conduit. And this is really interesting from a geothermal perspective, because what this means is that the hot material rising from the core mantle boundary, it doesn't just sort of rise in a uniform way everywhere. It means you get very concentrated hot areas, which means when they get to the surface of the Earth, we can get very concentrated areas of hot mantle underneath your feet. So consider this spot just here. If you can see my cursor, let me see if I can get a laser pointer. Just here, we have this hot material rising from the mantle up to the surface. Where that reaches the surface of the Earth, we'll get what we call a hot spot. And these hot spots are places like Iceland, places like Hawaii, where we have lots of volcanic activity in the middle of the oceans, or in the middle of a tectonic plate. And where you have lots of volcanic activity, you get a lot of heat at the surface. So I'm going to change track a little bit now, and I'm going to think about how we can use this knowledge to understand some processes that can help us with greening mining. So this was a little bit of a diversion, but I just wanted to give you a bit of a background as to how the Earth transfers heat, why some places are anomalously hot, some places are anomalously cold, and so on. And why this is really useful is because it means that we have this wide array of different temperatures in the mantle and in the crust beneath our feet as we walk around the world. So some places are very cold, some places are very hot. And this is all because the mantle is very complicated, can flow over time. And that's where I've spent a lot of my work looking at. So from this process to geothermal heat flow and to green mining. So this is a rather nasty looking slide. I don't expect you to read all of it, but this is just to show you kind of the workflow that geologists go through typically to find a new mining prospect. So first of all, we might do complicated labor-intensive geological mapping where geologists go out into the field and they look at the rocks and make measurements. Then we might do a whole bunch of very expensive geophysical surveys. Then we might do a whole load of geological modeling and all sorts of things just to find one very small mineral deposit where you happen to have concentrated copper or concentrated rare earth elements or something like that. This is very expensive, very time consuming, and very prone to misses. So you can put all of this effort in and find nothing very easily. And ultimately, the goal here is to find a mineral deposit and then dig a gigantic hole in the ground to extract that resource. So this is the Kennecott copper mine in just outside Salt Lake City in the USA. This is probably I think it is the oldest open pit mine in the world. It's about 120 years old and it's still active. It's one of the world's biggest suppliers of copper and silver. But as you can see, very environmentally destructive. It's a massive hole in the ground for a start. And think about all of that material that's being extracted. That has to go somewhere. You can see some evidence of that. There's these tailings heaps located all around the mine. All of that material is going to be exposed to the atmosphere. Rain will leach the material and cause acid mine drainage and all of this sort of stuff. And then ultimately, we're only actually going to be interested in extracting maybe at best 0.5% of the material that's dug out of this hole. So maybe if you're lucky, 0.5% of that material will be copper, silver, molybdenum, and other metals that you're interested in. So it's very wasteful, very environmentally destructive. So what I got wondering, with some work that I did at the University of Oxford, and this is primarily work that was carried out by the co-founders of Ascension Earth Resources, is whether rather than digging gigantic holes in the ground, could we use geothermal heat flow and volcanic activity to shortcut this very, very environmentally destructive process? And it turns out you can. So what's really interesting about these volcanoes is, first of all, they often form in these locations where we have mantle upwellings, where we have very hot mantle domains just beneath the Earth's surface. And what's also really interesting about them is when they blow all this material into the air, they're actually wasting a lot of quite useful stuff that we could make a use of. So they're blowing into the air copper, silver, tungsten, lead, zinc, antimony, neodymium, molybdenum, all sorts of things. And you can say, oh, well, okay, great, they're blowing all that into the air, but presumably at really, really low concentrations. Well, not actually. So if you look on the x-axis of this diagram here, we have the global mined metal production. So this is, if I go back to this, is the amount of stuff that comes out of, that humans dig out of holes in the ground that look like this. And on the y-axis, we have the total amount of material in 1 year that volcanoes blow out of their vents. Okay, so amount of material that we're digging out of the ground to use in our everyday stuff, so making pots and pans and cars and buildings and all that sort of stuff. And then the stuff that's just naturally blown out of volcanoes in this way every year. And you can see that there's almost a one-to-one relationship between these two things. And actually, if anything, the black line is a one-to-one relationship. Most of these points sit above that line. So every year, a volcano, if you sum over, add together all the stuff that's blown out of every volcano, there's actually more stuff blown, more of these critical materials that we use in our everyday lives blown out of volcanoes than is mined by humans. So the big question is, can we somehow access this stuff either in volcanic products or even before it's blown out of a volcano, so that we don't have to sort of post hoc wait for the Earth the geology to naturally concentrate these elements and then dig a hole in the ground? So this is typically what happens. So this is a sort of an ancient volcano. We have a sort of plumbing system down here. So this is the surface of the Earth at the top here. Then as we go down, we're going to the volcano's plumbing system. Then very deep, maybe 30 kilometers beneath that, we have that hot mantle that I've spent a lot of my career worrying about. And I told you about in the first half of this talk. And the magma rises through the Earth and then it erupts out the surface here. And then when that volcanic activity has stopped over millions of years, the Earth naturally concentrates a lot of this stuff for us. So we get all these strange composition, altered stuff. And then somewhere in this kind of plumbing system, there'll be a little area where we have very high concentrations of copper or silver or gold or something like that. And that's just a natural process. The Earth kind of accidentally concentrates this material over time. And those big holes in the ground target those small deposits and they mine them. Now the question is, can we directly access this plumbing system without having to wait for all that alteration and then to have to dig a hole? So can we avoid this? And at Ascension Earth Resources, we're particularly interested in a group of metals that have been in the news a lot recently called rare earth elements. And these are, so this is a periodic table. Often the periodic table, when you look at it in a classic view, doesn't include these two rows at the bottom. It includes everything else, but there's actually this sort of pull out in the periodic table. And these are the rare earth elements. And they're very exotic sounding things. So to pick a few out for you, neodymium, praseodymium, europium, palladium, terbium, dysprosium, they're probably things that you've never thought about before. I hadn't thought about it until I got involved in this. But they're actually critical minerals used in predominantly in magnets, actually. So magnets are made of iron and steel, but they're actually quite heat sensitive. They stop working when temperatures get high, and they're often very heavy. But it turns out if you add a little bit of one of these rare earth elements, you can make them much lighter and make them less heat sensitive. So they're super useful. But mining for them is a big problem because they're not found in very high concentrations at all. So all that natural concentration process that I just told you about is great for things like copper and nickel and zinc, but really difficult for this sort of thing. It's very difficult to find these naturally concentrated deposits. So what we're looking at Ascension is focusing on recovering metals that are essential to advancing green energy technologies in an environmentally sustainable way. And we're doing that using natural geothermal heat and volcanic rocks. So this is a picture from Iceland where there's a geothermal power station harnessing geothermal energy. So drilling 2 kilometers down into the earth, producing really hot water that turns to steam when it gets to the surface so you can use to power a turbine. We're going to harness this energy instead of for generating electricity to help us access metals. And how this works is somewhere near to a volcano where we've had all this erupted material produced that contains all of those metals, but in low concentrations. We drill 2 holes in the ground. We have a tank full of water. We dose that water with something that we call a lixiviant, which helps to dissolve metals out of rock. We pump that water into the subsurface. We flow it through this green layer here, which is a volcanic rock rich in all those metals, naturally rich in metals produced from that volcano. And then we produce that fluid over here. And then our fluid is rich in rare earth elements and other critical minerals. So it's a really simple process. This is basically exactly the same as what geothermal power companies do. It's just all they're interested in is the heat. We're just dosing the fluid with something to help liberate some of those metals that otherwise would accumulate quite slowly, so that we can produce higher concentrations of metals at the producer well. And this kind of happens naturally in geothermal power production already. So this is a geothermal well. So all they're interested in here is producing steam, but by accident, they produce all of this scale as well. So this is so it's a bit like, you know, if you're from a hard water area like we are in Oxford, when you boil your kettle lots of times, you'll get lime scale in your kettle. Geothermal power companies also get this problem because they pass fluids through rocks, and then when they bring the fluids up, it scales on their well. And it turns out this scale actually contains about 1% silver. So this is really rich in critical minerals. Now, when it scales on the well, that's not very useful because you can't flow stuff through it very well. But if you can produce that fluid to the surface, you can instead extract the metals from the fluid once they've been produced. And that was what we were actually looking at on Ascension Island when I was there just last week and at the end of last year. So Ascension Island is a volcano. It's an ancient volcano. It's still dormant. The last eruption there was 500 years ago. And actually in the distance here, this kind of dark coloured patch was the last eruption 500 years ago. And it has rocks that are not particularly rich in critical minerals. You would never want to go and dig an open pit here and crush all the rocks and everything. You just wouldn't recover enough. But if you use this new technology and leach the material underground, you can concentrate the metal in the fluid in an environmentally friendly way and access a resource that otherwise would not be accessible. So from the UK, from RAF Brize Norton, we flew to Ascension Island in the, they call it the South Atlantic. It's actually pretty much the equatorial Atlantic. It's a place that kind of found fame in the 1980s because of the Falklands conflict. It was a stop-off point for refueling and resupplying the vessels. It's actually really interesting. They have, on Ascension Island, on average, they have about 2 to 3 flights every week. 2 from the UK, 1 from the US, and 1 from St. Helena. During the Falklands conflict, they were having about 300 flights per day. So it was briefly the world's busiest airfield during the Falklands conflict. It must have been a remarkable time to be there. So this is Ascension Island. There's the airfield. It's got a mountain in the middle around 900 meters high called Green Mountain. Green Mountain is actually fascinating. It's not naturally green. It was completely barren when it was discovered. But the Royal Navy was garrisoned there to prevent Napoleon from breaking out of exile on St. Helena, because he had a kind of a habit of breaking out of exile. But there was no water. So Charles Darwin and Joseph Hooker suggested planting a rainforest on the mountain, which they did. And they started with bamboo and other water hardy plants, and they actually made it rain. So it never used to rain ever on Ascension Island, and now it rains pretty much every day. And that's entirely because of this terraforming that was done in the 19th century. So on the top of the mountain, there are banana forests, and there's a bamboo forest on the summit of the mountain. I should have put a picture in it. There's no view from the mountain, it's dense bamboo. And there are these rain catchers for catching the water. So all of this grass is invasive. There was no grass on the mountain at all. It was just brown and barren. There's also a bunch of wildlife. So here's a masked booby. It's a really, really interesting place. From an environmental perspective, these birds were almost wiped out by rats and cats, which have been since removed. It was also actually where the first messages from the moon landings in 1969 were returned to Earth. So the first people to know about the moon landings were on Ascension Island. And in the 1980s, there was extensive drilling on Ascension Island for geothermal power. This never went anywhere because NASA left the island and the demand for power actually really, really decreased. But there was extensive drilling for geothermal power. And what they discovered is actually, by accident, they didn't sort of analyze the rocks, but they discovered that the rocks there are reasonably rich in rare earth elements. And they drilled a bunch of holes all around the island. It was actually a huge program. It must have been very expensive, funded by the US Department of Energy. And the wellhead for one of those wells is still there today. So this one here. And what we're proposing is we could inject fluids, allow it to heat up, dissolve metals out of the rock, and recover it to the surface, and provide a UK source of critical minerals, a sovereign source of these rare earth elements. The supply chain of these rare earth elements is currently completely dominated. 90% of the supply chain is dominated by China, which is why they're in the news so much at the moment, because it's generally considered a bit of a national security risk. The UK have no current supply chain of rare earth elements. So we went to the core sheds. This is actually in Utah. My colleague Olivia Hogg analysed all of this core from the drilling in the 1980s. We collected samples, recorded the compositions of all of these rocks, trying to find target horizons that we could flow the fluid through. And the types of rocks we're looking at are these rocks here. This is a volcanic tuff. So these are formed in these very explosive eruptions. The magma kind of blows itself into tiny fragments, and when it settles, you have a very, very porous rock that you can flow fluids through. My colleague Mike Kendall is pointing at a particularly interesting layer there. And when we're on the island, we carried out a bunch of geophysical imaging surveys. So this is this is a circuit diagram with the Earth instead of a sort of a resistor. So what you can do is you can pass electrical current through the Earth and measure the voltage and measure the current, and that tells you about the resistance of the rocks underground. So we laid a bunch of cables in Ascension Island, hammered in metal electrodes, passed current between the electrodes, and used that to calculate how resistive the rocks are. And if you have a conductive blob underground and a resistive blob underground, when you pass current through the rocks, you can work out where are the conductive blobs, where are the resistive blobs. And this can help you to understand the layering of the rocks in the subsurface. It's a bit like putting the Earth inside a CT scanner. So you have in a CT scanner, you have a electromagnetic source around your body. They pass electromagnetic waves through you and measure how fast and how absorbed they get as they pass through. We're just doing the same thing with the Earth, actually. It's very, very similar to that. And this allows us to image the subsurface, work out where those layers are that we might want to pass fluids through. Another thing we can do is seismic imaging. So instead of conductive and resistive blobs, we can have fast and slow blobs. So these are rocks that transmit seismic energy very quickly and blobs that transmit it much more slowly. And if we have a bunch of sort of seismic sources, these might be small earthquakes, they might be someone stamping their foot, they might be a plane taking off, something like that. We can measure how long it takes for the energy to get from those sources to the receivers. If we have lots and lots of paths, we can then calculate, again, where the fast blobs are, where the slow blobs are. And that allows us to image the subsurface. We deployed a bunch of instruments all around the island, and we're currently analysing the data from these to look at what the subsurface structure looks like. And we're interested in particular in this area here. We carried out a bunch of surveys along the roads here as well. And this is kind of what one of those images looks like. So this is a subsurface resistivity image. So we have cables. This is a panorama along this road here. We have cables with electrodes knocked into the ground. And the red stuff here is resistive material in the subsurface. The blue stuff is conductive material. So the surface of the Earth is up here, and this is depth below the surface on the y-axis. And as you go from the surface down deep into the Earth, you can see that we have these resistive material, which might be really, really tight, impermeable rocks, so you can't pass a fluid through those. And then the rocks at depth there, those are probably saturated in water, so they're very conductive. So that's the kind of image we can build up. I'll just skip over that slide there. And all of this together is allowing us to build up this picture of where are these very permeable volcanic rocks that we can pass fluids through, accelerate mineralization, and produce critical minerals. So that's just a bit of a taster of my career and how I've moved from looking at geothermal heat flow from a very kind of high-level mantle convection perspective all the way through to where it's taken me to these practical cutting-edge kind of metal recovery technologies in this new spin-out company. So I'm just going to leave you here with this picture of a nice but rather sad-looking donkey on Ascension Island to finish. So thank you very much for your time, and I'm happy to take any questions. I think you might be muted, Mary. I can't hear you.
Yes, I did mute myself, thank you. Thank you very much for that, Simon. We've got some questions starting to come in. And the first one is, does the concentrating process carry an enhanced risk of pollution if the extraction percentage isn't near 100%?
Yes, yeah, that's a really good question, really important question. It's something we're talking a lot about to the government and the community on Ascension Island last week. So clearly we don't want to be drinking rare earth element enriched fluids. That would be really bad. So the technology we're developing is very carefully making sure that we don't lose fluid to the surrounding area. So what we do is we always over pump. So anything we produce, anything we inject, we suck out maybe 10% more. So what that means is that all of the ambient fluid from around the area will be moving towards the producer well. So that reduces the risk of your fluid escaping and traveling into kind of known areas.
Mm-hmm.
Something else you can do is you can have monitoring wells around your injector and producer. So if you do lose any fluid, you can detect that quickly and put a stop to it. We'll also be using these kind of monitoring techniques to monitor where the fluids are. So something that's really useful is that when your fluid becomes enriched in rare earth elements, it becomes very electrically conductive. So salty water is more conductive than pure water because it has all those dissolved ions in it. And on these resistivity images, you can see the more conductive areas and monitor where the fluid is to make sure it's not disappearing off in the wrong direction. And finally, the rocks naturally neutralize the fluid. So as the fluid moves through the rocks, it starts off as maybe an acidic solution. As it moves through the rock, it interacts with the fluids, and the rocks move towards a more neutral composition. So there's kind of this natural, we call it buffering, natural buffering that actually moves the fluids from being environmentally damaging to being environmentally benign. And the final point is the idea of pumping these fluids into the ground sounds perhaps slightly scary. It's worth noting geothermal companies actually do this already to descale. So all that scale on their wells, they pump in some acids to descale, and water companies actually do this as well to descale their wells. And mining companies also face all of these problems. So if we go back to that huge open pit mine here, the bottom of this mine is well below the water table. And in Utah, water is actually reasonably scarce. And there's a big lake, this Great Salt Lake. So water is abstracted from this water table. So the mining company here has to make really sure that they drain all of this water and they don't allow any of this nasty material that they're leaching to contaminate the water table. So sorry, that's a very, very long answer, but yes. These solutions are somewhat toxic, but there are lots of stages in place to make sure that that's not a problem.
Yeah, just picking up on that, Simon, we've got a question about what kind of chemicals are injected into the wells. Now, I would imagine some of that might be sort of commercially sensitive, but is there anything you can tell us about that?
Yeah, so they're acids and bases. That yes,
Okay.
they're commercial. It is commercially sensitive. So I can't tell you exactly what, but I can tell you that in the pH of the fluids that we're looking at are sort of in the range sort of fairy liquid and lemon juice.
Okay.
So not things that are inherently scary, stuff that you'd be happy to get on your hand and so on.
Yeah.
And as they move through the rock as well, the pH gradually reduces.
Okay. And I guess just a thought from me is, when you actually push the fluids through, is it a gradient in terms of having to keep pushing it through the same area? Because obviously it takes a while for things to come into solution.
Yes, so there's as the what's the slide? As the fluid moves through this layer, the fluid composition will be evolving all the time as it moves through. So the reactions that happen near to the injector well will be quite different to the ones that happen at the producer well. So the recovery perhaps near to the injector will not necessarily be the same as the recovery rates of the producer. So it's an ongoing thing. You cycle this many times. You do it over quite a long time period to make sure you get this kind of even recovery all the way through the rocks. You might even reverse the flow and inject over here, produce over here, and so on. Wow.
And I guess it's sort of you don't just pump it through constantly, I suppose. To a degree, you have to almost let it steep and sort of come out of the rock, or are you constantly moving the fluid?
Exactly. We will be trying to constantly pump it because if you pump it in and leave it, that's when the plume can kind of sort of spread a bit.
Of course,
You
yeah.
lose control of the fluid slightly,
Mm.
not very quickly, but that can happen. If you're always pumping, you're always making sure you're controlling the direction of the fluid. But the idea is that you do leave the fluid underground for long enough to let it steam, yeah, and cook under these geothermal. So yeah, this process only really happens on a useful timescale if you have geothermal heat as well. Um, so you need a volcano to produce the rocks,
Mhm.
and you also need geothermal heat to allow the process to happen quickly.
So you need probably dormant rather than extinct volcanoes because of having the heat source.
Yeah, so they could be extinct, but they would also coincidentally also need a geothermal heat source as
Yeah.
well. So maybe that's because they only recently went extinct, or there's a there's a mantle upwelling that's heating the rocks coincidentally as well. But active volcanoes are better.
I mean, I guess sort of dormant and extinct is a very human concept, really.
It is exactly, yeah. If they went extinct, a few 100,000 years ago, the rocks are probably still pretty hot. So
Mm.
yeah.
Okay. And we've also got a question as well about, um, yeah, it looks on the one image like it's a road that you've got the cables running down. Now, I would imagine roads in Ascension Island is a fairly loose terminology because that didn't look like a metalled road to me. But yeah, roads are where they are for for obvious reasons. Does that put any bias into the results, or is it a case of that image just happens to be on a road?
Um, yeah. So actually, this is a really interesting point. So at Ascension and University of Oxford, we're all kind of research scientists who have sort of recently moved out into the commercial world. Um, when we went to Ascension Island this time, we took with us a couple of colleagues from Marriott Drilling.
Mhm.
So they're a drilling company who drill a lot of geothermal wells. Um, and one of the critical things for drilling is access. So it does bias our results. We might have a fantastic resource somewhere that's 200 kilometers, not on Ascension Island, but say in Tanzania or something, 200 kilometers from the nearest roads. Now that's going to be a problem
Mm.
uh, for all sorts of reasons, access, power, everything like that. So we are quite constrained to. You don't have to be on a road. You can cut a track and access, but yeah, and also for this geophysical imaging, there's a
Mm.
lot of cable. There's a kilometer of cable here, uh, 80 steel electrodes. It's all very heavy. It's much easier if you can do this where there's a road.
Mm.
So it is a bias, yeah, for sure. Yeah.
Okay. And there's a couple of questions as well of you're talking in the future tense, obviously this is cutting edge stuff. Do you have an idea as to when this is actually going to start being used commercially, or will you do tests to start with? Where are you in the process?
Yeah. So at the moment we're at lab level. So in the sort of spin out startup world, then we use these kind of sort of NASA technology, actually technological readiness levels,
Hmm.
and you move from lab level to eventually to production in the real world level.
Hmm.
We're very near the start of that workflow at the moment. So we're working on lab scale, and then you'll move through the technological readiness levels, kind of to looking at operational levels where you do go and drill some holes, but you're injecting just pure water or maybe a tracer to map where the fluid goes, but it's completely inert. So
Hmm.
we're not injecting that, like we're not injecting chemicals producing metal-rich fluids
Hmm.
because that carries an environmental risk. So you just do that with inert fluids, and we're looking to do that potentially next year.
Hmm.
We've got a few projects on the go there. And then injecting chemicals is the next step. Once we've done a rigorous environmental impact assessment and got permission from regulators and all of that sort of stuff,
Hmm.
that probably won't be till the year after. So it's long term. Full scale production won't be for many years. Yeah. So this is
Okay.
it's a development process.
Okay. Right. Next question is how deep are your electrodes for resistivity?
Oh, there. sort of, I don't know whether you can see me, but sort of that long. They're maybe 10 inches. So no, maybe more, 15 inches perhaps. You knock them into the ground so there's maybe an inch sticking up. So
Mm,
they're very short. You just It's quite difficult here actually because it's so dry
mm.
to get really good contact between the rocks and the electrode.
Of course, yes.
Um, but yeah, so you can have longer ones to help you with that. But knocking 80 sort of meter long electrodes into the ground is it's pretty time consuming and tiring. So there's a trade off.
So even terraforming hasn't helped you to that degree yet.
Not to that degree, and unfortunately, it's still quite dry down on this plateau. It's wet up at the top, but
Mm.
we wouldn't be able to do this up in the mountain because it's too. We need quite flat terrain.
Okay. Right, and there's a question here is, are other countries doing this sort of research? About 6 to 8 years ago in Ferney-Voltaire, France, next to Geneva, there were small devices buried slightly in the ground every few hundred yards, say. The person's daughter lived there and reckoned there was some kind of radiation detector with a view to a useful heat source. Does this sound more like geophysics to you?
I can't say for sure. It does sound a bit like geophysics. Yeah, yeah,
Okay.
yeah. So it could have been a sort of ongoing resistivity survey. This is a very routine technique. We're using it in a slightly more novel way here, but
Mm,
it's used very commonly for things like monitoring acid mine drainage. So it's done quite commonly in places like Cornwall, where there's a lot of tin tailings from ancient mining,
mhm.
uh, and all around the world for that landfill monitoring, imaging the water table, and all this sort of stuff. So it's a very common technique.
Okay. And we've got a question here is there a danger of inducing earthquakes? I mean, I'm guessing that by the amount of water coming through, you're not talking about drastically altering the structure of the rock.
Yeah, so there is a potentially a small risk of that. We would not want to be doing this anywhere where there are faults. So faults are these kind of places where because the Earth's crust is quite brittle. If you stretch or deform the surface of the Earth, it breaks brittly along these concentrated fault plains. We wouldn't want to be doing this anywhere where we knew that there were faults because they can be permeability pathways as well.
Mhm.
So
Yes.
fluids can motor along them and disappear to somewhere we don't want them to be. And there is a risk of inducing seismicity on those faults. And so we would, if there are faults there, we just won't go near it. And that would be the time it would induce seismicity. Another aspect that as you move the fluids underground, you'll some kind of seismic energy will emanate from the fluid as it goes through the earth.
Mm.
It won't be detectable to humans, but we will have an array of seismic stations monitoring, highly sensitive stations monitoring that sort of energy change because you're changing the physical properties of the rock as you leach them.
Mm.
So we will be monitoring that, but we don't envisage earthquakes that will be detectable to humans. We're not fracking. So fracking, we
Mm.
absolutely don't want to fracture the rock. Um, so fracking deliberately pumps at a pressure high enough to fracture the rock. And as you fracture the rock, that's when you get earthquakes, and we won't be doing that. So
So basically, another question talks about is there a bigger risk of things like landslides? But from what you've just said, I think that probably minimises that risk.
yes, I think so. Yeah.
Okay. Right, so the next one is interesting given the political landscape of the world at the moment. Does the technology have any relevance to mining rare earths in Ukraine?
Um, Not directly.
Hmm.
So interestingly, so we call this in situ leaching. So where you pump a fluid in, leach the rocks in place. You don't dig them up and move them.
Mhm.
So traditional mining, you dig the rocks up, crush them, move them somewhere, then leach them to get the metals out. We're just cutting all of that out and leaching them in place. And actually, the vast majority of the Earth uranium supply is actually mined in this way,
Wow.
and has been for a long time. So in Arizona, there's a mine that does this. I think it's closed now, actually, but there was. and Kazakhstan, various other places. There are these in situ uranium leaching facilities. The technology is very different for those, but the principle's the same. Copper can also be leached in this way and is leached in this way. They don't use geothermal heat. It's a different resource,
Oh,
a bit
okay.
different. But so in Ukraine, I don't think that there aren't the rocks there are not the right type for this type of technology. They might have uranium resources where they could use this technology, but my understanding of that sort of stuff in Ukraine is that this would be a traditional mining approach where you look for these naturally very concentrated deposits, which are really hard to find for rare earth elements. And then you dig a hole and you pull them out. Or you sink a shaft and mine them underground. That's quite distinct from our technology because we're targeting a completely different resource, which is low grade, laterally extensive. And on that as well, I'm just, because of the nature of those deposit types, they're very concentrated. If you look at a map of Ukraine, there's a lot of Ukraine, and these deposits are, they might only be a kilometer by kilometer. They're all covered by farmland and steppe. I don't think we know if and where these deposits exist, to be perfectly honest. So it's highly speculative, all this stuff you're hearing about Ukraine, but it's also traditional mining, not this in situ leaching that we're talking about.
Okay. So, I mean, obviously bearing in mind that, a lot of the heat from the Earth in the centre comes from radioactive decay, as well as sort of just the general friction and so on over time. Does natural radioactivity have any impact on heat flows?
It does, yes. So I kind of ignored that actually, but most of the Earth's heat. So interesting story actually. So Kelvin in the 18th century, Lord Kelvin, he tried to calculate the age of the Earth from the Earth's temperature, and he calculated that the Earth was a few tens of millions of years old. That's because for the Earth, for the surface heat flow to be what it is today, the Earth must have formed a few tens of millions of years ago. What he missed is that the Earth generates a lot of its own radioactive heat. So in the mantle, there's not very much uranium or potassium and so on, but there's enough because the mantle is very, very thick to generate quite a lot of radioactive heat. And when you factor that in, that's kept the Earth hot for 4.5 billion years. So most of the Earth's heat actually isn't residual from when it formed, is from radioactive decay. Now, on another level, you might have heard a bit about geothermal power in Cornwall. So United Downs and Eden, the Eden project, are two geothermal energy projects. And actually United Downs is, in theory, about to produce electricity in a few months' time. Cornwall isn't one of those places where there's a mantle upwelling and the Earth is naturally very, very hot. But in Cornwall, there is a lot of granite. And granite is very rich in potassium, and there's one isotope of potassium which is radioactive. And that means that the Earth is naturally hot in Cornwall, which makes it geothermally prospective.
Okay. The question here is, are there recoverable amounts of rare earths from tailings of present mines? Now,
Yes, there are. Sorry.
Go on.
Yeah, that's a really interesting question. So we have a project partner that we work with called Soloxium. They're another spin out from Oxford University. But they work on mineral separation, and a big customer for their technology is in situ leaching of old mining tailings. Yeah. So this is potentially slightly more environmentally risky because these tailings are at the surface. So you would be pouring chemicals onto those tailings at surface conditions. Maybe you do that in a controlled environment. You dig the tailings up and do it somewhere controlled. But these are they're at the surface.
Mm.
Another company I met with a few weeks ago is a biotech company who have developed plants that you can plant on tailings, and they actually in their plant structure they fix rare earth elements. So you kind of it's like mowing the lawn. You kind of harvest these plants, and you can separate the metals back out of the plants. And so there are lots of people actually working on this because you know the Victorians and the Georgians and Romans even the grade of mineral resources they were looking at is much higher than what we have access to today,
Mm.
because most of those high grade material has been mined. So they actually threw away quite high grade material. So sometimes slag heaps and tailings piles can actually be quite rich resources.
So, just thinking about it, one of the things I did hear was that some of the slag heaps or waste heaps from the tin mines in Cornwall have been found to have quite high levels of lithium in them. So I'm guessing you could almost apply this kind of technology to that waste.
Yeah, potentially. Yeah, I don't. That is potentially true. There's also a company called Cornish Lithium who are kind of a flag bearer for this kind of technology. They are they're a lithium producing tech company, and they are planning to recover geothermal heat with lithium resources. So I was talking about having to pass these fluids through
Mm.
volcanic rocks and leach the metals out of them. Lithium is so keen to jump into the fluid. You don't even have to dose the fluid with anything. They
Really?
just go into the natural geothermal fluids. So their plan is it's called direct lithium extraction, and this is done around the world actually, and particularly in Germany and North America. You produce geothermal fluids, use the fluids to generate electricity or district heating, but you also recover lithium from those fluids directly. Yeah, and potentially tailings as well also contain lithium that could be leached in that way.
I may be going beyond your part of the processes, so forgive me if that's the case. Once you've got the fluid back to the surface, how do you then get the minerals out of the liquid? Is it evaporation or how do you do it? Do you know?
Yeah, so there are actually several ways of doing this. Some of them are quite dirty, and some are less so. Basically, you either have electrodes or some kind of membrane that uh, rare earth elements are kind of attracted to,
Mm.
and you pass the fluid through this membrane or pass these electrodes, and every time you cycle the fluid through these membranes and electrodes, kind of they take a certain proportion of those
Mm.
elements, and then you do it again and again and again until you end up with a relatively clean fluid and the metals have been extracted.
Mhm.
That's the normal way of doing it. It can involve dosing the fluid with quite nasty chemicals, which is something we want to avoid. And
Okay.
it's actually one of the reasons that a lot of this stuff is done mostly in China, because their environmental regulations are more permissive, let's say.
Though I did read something interesting about even one of the Chinese ministers had admitted how environmentally damaging their own processes and rules were, which I thought was quite a vocal comment for somebody in his position, to be honest.
Yeah, so the way that rare earths are extracted in China is very environmentally damaging. They're
Mm.
called ion adsorption clays. They're they're, they're probably initially volcanic rocks that have been subjected to um, weather for millennia, for millions of years,
Mm.
and that the rain and surface conditions have gradually enriched rare earths in these deposits, and then basically they just go and pour acid on them, and then that flows through, the surface layer, and then they pump those acids out, and they're enriched in rare earths, and then the separation process involves more acids, and it's a nasty process,
Mm.
and we need to move away from that. Really, the Chinese seem happy to do this at the moment, but they shouldn't be really. So we we need a better way to do it. So
Yeah.
that's what we're going to
Uh,
do.
And the way you sort of explained with the electrodes and the membranes, are they selective? So basically that helps to separate out the different elements as you go through the process.
Yeah, it's actually really so you can separate. So if I go to the where is it? Periodic table. Yeah, here. So if you take sort of one of the elements at this end, lanthanum or something, and one of the elements at this end, lutetium. So lutetium is what we call a heavy rare earth. Lanthanum is a light rare earth.
Mm.
Um, you can you can get all of the rare earths out of the fluid without too much difficulty, and then you have what's called a mixed rare earth, you know, mixture, if you like. It's then relatively easy to separate this end from this end.
Mm.
What's really hard to do is to separate, say, terbium from dysprosium.
Mm.
They're both really heavy. They both have similar charges, so that the kind of the fractional difference between them is tiny. So if you compare helium to dysprosium, they're completely different.
Mm.
But these two things come together. So if you really want to separate terbium from dysprosium, you have to have a very bespoke process that you cycle many times to gradually separate them out from each other. It's a painful process.
Yeah, I can imagine.
Luckily, you don't often need to separate out these two from each other. It usually is okay if they just come together, but sometimes you do. So
And do you have, I guess it's very difficult to say how much you're going to get back because obviously that depends on the local geology and the geochemistry. But what kind of concentrations are you looking at applying this kind of technology to?
the rocks we're looking at, so the iron adsorption clays, which are kind of the standard, the concentrations are 150 parts per million neodymium. So if you add together all of the rare earths, I'm not sure, maybe 1,500 parts per million. So 15 parts per thousand, or 1.5 parts per thousand rare earths. Maybe a bit more than that. We're looking at similar concentrations, maybe a bit higher. On Ascension Island, it's a bit lower, but yeah. So those are the concentrations in the rocks.
Mm.
For traditional mining, digging a hole in the ground, these are not economic quantities. That the cost of doing that is so high, it's not worth it. So you have to have a different technology. So the deposit types that you would use for traditional mining are quite different to this.
So, and we've got a question here as well about recycling rare earths and compounds from existing devices. Do you think this kind of technology or the separation side of it at least could help us to reclaim some of those rare earths?
Yeah, so that's really interesting as well. So because separating because separating out these metals is really hard, and they're used in tiny, but like in these magnets, they're used in honestly tiny quantities. They make a huge difference to the properties of the magnet, but they're used in teeny quantities. It's simply not economic at the moment to extract them. So yes, possibly you can recycle the magnet as a whole block. That's probably more tractable. But getting the dysprosium out of a magnet you've put in a wind turbine, very difficult to do. In a fighter jet, it's used in a tiny quantity. The magnet itself is used in a tiny quantity, etc. So yes, recycling is possible, not commonly done because of that. The other thing is that these technologies are actually quite modern. So lots of the devices that these technologies are in that require these minerals just haven't reached the end of their life yet.
Yeah.
So there's nothing to recycle in that sense.
And I guess to a degree, we need to find ways to build them that help them become more recyclable at the end. It's
Absolutely,
not
yeah.
called rare earths for nothing, are they? Obviously, we have a growing population, a growing need for these devices. So at some point, there has to become an economic point, hopefully, when we can recycle more.
Yeah, yeah. So yeah, we do need to start thinking of building things with recycling in mind for sure. And what's interesting about rare earths is they're not actually that rare.
Ah,
they're, any rock that you pick up, it contains rare earths, often in very low concentrations. a few parts per million, but any rock contains them. They're everywhere in the Earth's crust.
But they're
It's
rare
just
because of the low concentrations.
exactly, yeah, yeah. Um,
Okay. Oh, yes, somebody's basically said we need better recycling and more durable and built with longevity in mind, which does tend to go back to the way things were done when I was a child, rather than sort of throw away, if you know what I mean. And I can see a lot of marketeers and businesses throwing up their hands in horror at that thought, but I think it is a bit of both.
but there is that still that interesting point that if you take a lithium battery for example, you can recycle a lithium battery. Um, the technology is not that good to do it at the moment, but there's no reason why it couldn't become better quite quickly. You can They are recyclable,
Mm.
but because we're only adopting uh, electric vehicles now, we're going to have to produce several billion electric vehicles probably
Yeah.
before we start recycling any of them in large numbers. So there's this big gap at the moment. Whilst we transition to a green economy, there's going to be a demand for stuff that just can't be met by recycling because there just isn't enough of it to recycle.
Mhm. I guess just thinking of recycling, that really does bring us round to the idea of circular economy, and hopefully at some point some of that will become more realistic.
Absolutely, yeah. So the question I think really is how do we produce these elements in a way that isn't environmentally disastrous?
Mm.
That's
No,
what we're trying to do.
I mean, obviously, yeah, the places we can use it at the moment are quite restricted because of the hydrology and everything else. But I think what you're describing is going to be a lot better, not only for the local environment, but actually once the elements have been extracted. Because on the surface of it, once the buildings are gone, it will return to the way it was, and there won't be any sign that you've ever done that industry.
Yeah, yeah,
Okay, just looking to see if there are any more questions. Oh, there are some questions as well. I know this is going way beyond the scope of the work you're doing, but I guess ultimately all these things are interlocked when it comes to these industries. Many phones do not have user replaceable batteries. Should this be a legal requirement? I think user replacement is a bit of a different
I,
thing given.
yeah. I don't have an opinion on that.
Yeah.
Yeah,
I
from
think
an
it's
environmental perspective, I feel like that's probably a good idea. But yeah, it's a bit beyond my area of policy, I'm afraid.
no, but thank you, Simon. That we've got no further questions at the moment, so I'll just give
Okay.
people a couple of minutes to say, if there's anything else they want to raise. I mean, I found that personally very fascinating, and I think the uses for rare earths we're still discovering. And it's a
Yeah,
case of it just throws it home to me that yeah, the world is a fascinating place, and there is so much for us to learn about it. I've
yeah.
got one here that says this technique seems to be a very good approach, not just for environmental but also economic benefits. Wish you every success. Fascinating talk.
Thank you.
Yes, and I've got a lot of people chiming in and saying thank you, excellent and very interesting.
Thank you very much to all.
So on that basis, as we don't have any more questions, I know that you're a busy man, so I'll give you 10 minutes back in your diary. And thank you so much for coming to talk to us, Simon. I really do appreciate it.
Thank you for the invitation. It's been great. Really interesting questions.
Yeah, and we've got comments saying very clearly presented and excellent and interesting. So people have really enjoyed it. Thank you.
Thank you. Have a great rest of your day, everyone.
Thank you very much, Simon.
Um,
Okay then.
Bye.
Bye.
yeah, thanks. Great. Yeah.
Okay then. Right, everybody. Thank you very much for coming along. I hope you did enjoy that. And next time we have Dr. Chris Rochelle from the British Geological Society survey, and he will be touching on geothermal, but he's talking about energy across the world in terms of how we use it purely as energy. So it ended up as a bit more of a common theme, but hopefully that will be of interest to you as well next month. Thank you all for coming. I'll see you next month, hopefully. Bye for now.